Carbon compounds are all around us, in our clothes, furniture, food, and body. To understand why carbon forms so many compounds, we need to look at bonding in carbon. In this lesson, you will learn about bonding in carbon and the different types of covalent bonds. At the end of this lesson, you will be able to list the properties of covalent compounds, explain the reasons for each of the properties of covalent compounds, list the steps for writing electron dot structures, classify the different types of covalent bonds, and explain covalent bonding in carbon with reference to methane. Covalent compounds are identified by some distinguishing properties. Let's look into the properties of covalent compounds. Covalent compounds have low melting and boiling points. This is due to weak forces of attraction between the molecules. For example, chloroform has a boiling point of 60 degrees centigrade. When compared to ionic compounds, covalent compounds are non-conductors of electricity. This is due to the absence of free ions. The type of bonding in the carbon compounds does not give rise to any ions. To understand the bond formation in carbon, we need to know the combining capacity of carbon. The combining capacity of any element depends on the number of valence electrons. Therefore, in order to know the combining capacity of carbon, we need to know the number of valence electrons in carbon. When we look at the electronic configuration of carbon, it is clear that it has to either gain or lose 4 electrons to attain noble gas configuration. Suppose carbon gains 4 electrons, it would form a C-4 ion. But carbon, being a comparatively less electronegative element than fluorine, chlorine, oxygen, etc., is unable to hold 4 extra electrons, meaning it would be difficult for the 6 protons to hold the 10 electrons. Now, suppose it loses 4 electrons, it would form a C+4 cation, which is again a difficult task. It would require a great deal of energy to remove 4 electrons, leaving the cation with 6 protons in the nucleus and holding only 2 electrons. This makes either of these possibilities difficult. Carbon overcomes this difficulty by sharing its electrons with other atoms of carbon or with atoms of other elements. We know that sharing of electrons results in a covalent bond, and the shared electrons belong to either of the atoms. This sharing helps in achieving noble gas configuration. The Lewis dot structures provide a picture of the bonding in molecules in terms of the shared pairs of electrons and the octet rule. A Lewis structure is a type of shorthand notation. In this method, atoms are written using their element symbols. Lines are drawn between atoms to indicate chemical bonds. Single lines are single bonds. Double lines are double bonds. Triple lines are triple bonds. Dots and sometimes the symbol X is used to represent an electron. Steps to draw a Lewis structure. Let's take carbon dioxide as an example in writing the Lewis dot structures. The first step in writing an electron dot structure is to locate a central atom. The central atom is the one with the lowest electronegativity. In carbon dioxide, since carbon is less electronegative than oxygen, it is the central atom. After selecting the central atom, connect the other atoms to it with a single bond. We may change these bonds to become double or triple bonds as we progress. So, Let us connect the two oxygen atoms with a carbon atom through single bonds on either side of it. The third step is to determine the number of valence electrons possessed by each atom in the molecule. In a carbon dioxide molecule, a carbon atom has 4 valence electrons and an oxygen atom has 6. Now the octet rule states that atoms with 8 electrons in their valence shell are stable. Hence, we need to check if the octet is satisfied for each atom or not. The next step is to arrange the electrons so that each atom contributes 1 electron to a single bond. Now, in the present example, when such an arrangement is done, we can see that there are 6 electrons around carbon and 7 around each oxygen atom. This means that the octet is not complete. As the octet is not complete, move 1 electron per bond per atom to make another bond. In this example, we observed that the octet was not completed. Hence, we move 1 electron for each, and now we see that both the carbon and oxygen atoms achieve the octet by forming a double bond between them. In a covalent bond, a shared electron pair is known as a bond pair. The bond pair is represented by a line between the bonded atoms. Depending on the number of electrons shared between the atoms, the covalent bonds are classified into 3 types: single covalent bond, double covalent bond, and triple covalent bond. Let's look at the formation of a single covalent bond, taking the example of a hydrogen molecule. We know that the atomic number of hydrogen is 1. Hence, hydrogen has 1 electron and it requires 1 more electron to attain the nearest inert gas configuration, which is helium. To achieve this, each hydrogen atom contributes an electron to form a single bond. Thus, a single covalent bond is formed between the 2 atoms of the hydrogen molecule. Considering the example of oxygen, let's see the formation of a double covalent bond. The atomic number of oxygen is 8, and it requires 2 electrons to achieve the nearest stable inert gas configuration, which is neon. To achieve this, 2 oxygen atoms contribute 2 unpaired electrons to produce 2 bond pairs. Thus, they share these 2 electron pairs to form a double bond or dicovalent bonds. Let us try it with nitrogen. The atomic number of nitrogen is 7, and it would require 3 electrons for attaining the nearest inert gas configuration, which is neon. Thus, the 2 nitrogen atoms combine together and produce 3 bond pairs and share the 3 bond pairs between them. Thus, a triple bond is present between the 2 nitrogen atoms in the nitrogen molecule. Now, let us take a heteroatomic molecule like methane and see the covalent bond formation in it. A carbon atom has 4 valence electrons. During the formation of a methane molecule, 1 electron of a carbon atom pairs with 1 electron of a hydrogen atom to form a bond pair. In this way, 4 bond pairs, which are 4 CH bonds, are produced. These electron pairs are shared by the carbon and 4 hydrogen atoms. It is important to remember that carbon is a tetravalent compound and one should always check for the fulfillment of tetravalency. In a covalently bonded molecule, like ethane, even though they have strong bonds within the molecule, the intermolecular forces between them are weak. Because of these weak intermolecular forces, ethane exists as a gas.